Hello, everybody, and welcome to the law of conservation of energy. Up until this point, we've looked at work, potential energy, kinetic energy, and now we are going to look at the conservation of energy. So let's start with the fact that, the law of conservation of energy states that energy. Ooh, I gotta change that. I did not realize. There we go. Energy cannot be created or destroyed. Energy cannot be created or destroyed, only changed from one form into another. So with the formula, I think it's a really easy way to see this. But first, we'll just talk about a couple of examples. The first one, example one, we're throwing a ball in the air, and it's kind of taking this path up and over, and then on its way back down. So we are looking at energy in terms of potential and kinetic. So if we make this height 0, height equals 0, then at the bottom, when we throw this, we are going to have a lot of velocity, a lot of initial velocity. So this will be basically all kinetic energy, or I guess we were using EK to begin with, right? All kinetic energy down here because that's our highest velocity. Then as the ball travels up this arc, it's going to slow down. And at the top, we're going to have no velocity. So it's going to take all of that kinetic energy and slowly turn it into potential energy because that's the highest height that it will have. H max. The highest height it will have compared to 0. So it's converted all that kinetic energy into potential energy. And as it starts falling down, it's converting that potential back into kinetic because it's slowly losing potential energy because the height is getting smaller, and it's turning that into kinetic energy because the velocity is getting higher. So in the middle here, we have kind of a mix of EK and EP. And then as it gets down to the bottom, it'll have all kinetic energy again and no potential energy. It's the same here with a pendulum. So this is, we've got a pendulum here, and then the weight on the end. And if you swing it back and forth, it takes that, that path I've drawn with a purple dotted line there. So I've got 3 different positions of our pendulum here. This is at the very top of its swing right here. And that's where it's going to turn around and swing back the other way. So in this case, at that moment that it's turning, it's got no velocity. Velocity is 0. Therefore, EK is 0. And obviously, we need to establish a reference point. So the bottom here can be our height 0. So that means we have all potential energy here. As that weight or that mass swings through, it's going to convert that potential energy into kinetic energy. So at the bottom, height 0, therefore potential energy is 0, and we have all kinetic energy at the bottom because that's when our velocity is the highest, is at the bottom of the swing, right? We've picked up speed coming down through the swing, we're moving the fastest at the bottom, and as we climb back up the other side, we're losing or slowing down. So our kinetic energy is going down. So kind of in the middle here, in this last position, we have a mix of sorry, I keep doing EP, mix of potential and kinetic, right? We're in that transition phase of switching kinetic into potential as we climb up, and as we climb down, we're switching that potential back into kinetic. Obviously, we're going to lose a little tiny bit of energy up at the top there due to friction, but we don't really talk about that much. So, yeah. So this happens because gravity is a conservative force. If there is friction, the energy is lost. So if there's any friction in the system, we do lose energy to friction, and friction creates heat or thermal energy. So we would slowly, I mean, obviously, if we had this pendulum here and we picked it up and swung it, it would slowly come to a stop. And that's due to the friction in the where it's tied up, and also there's air friction. So we are losing energy to heat into the environment, but we are dealing more with perfect scenarios here, so we don't have to worry about that too much. So yeah, friction converts energy into heat or thermal energy. So the formula that we're dealing with is energy initial is equal to energy final. So the energy initially should always equal the energy final, and you can break that down even further because energy initial can be energy kinetic initial plus energy potential initial, and that has to equal energy kinetic final plus energy potential final. And then you can even go one step further and say, well, kinetic energy initial is 1/2 mv initial squared plus energy potential initial is going to be mgh height initial, and that will equal 1/2 mass velocity final squared plus mgh final. And that is kind of, you can start anywhere here, but that's kind of how you set it up. So because conservation of energy, we know that the energy initial has to equal the energy final. From there, we can expand outwards. Well, let's put this into practice. So here we have a 65 kilogram snowboarder starts at rest and travels 65 vertical meters down a hill into a gully and 45 vertical meters up the other side. What is her speed at this point? So it's going to look something like this. So the snowboarder starts up here, 65 meters, so let's say above the gully. So let's make this, I don't know what happened there. The bottom of the gully will make height 0 meters. So we know that at the top here, this is 65 meters. And then when she gets here in our final spot, she is 45 meters above our 0. So let's do our formula. E initial is equal to E final. Energy kinetic initial plus energy potential initial is going to be energy kinetic final plus energy potential final, which is 1/2 mvi squared plus mgh initial is equal to 1/2 mv final squared plus mgh final. So now we need to ask ourselves, is there any of these that we can eliminate? And we probably could have done that in this step here, but because the snowboarder starts at rest, that means this is kind of our initial point here, and this is our final point. So at the initial point, we have velocity is equal to 0. She's starting from rest. So if her initial velocity is 0, that means that whole term, that 1/2 mvi squared, goes away. It is 0. So now we can rewrite our formula. mghi is equal to 1/2 mv final squared plus mgh final. The really cool thing about this is that you have a mass in every term here. So you can simplify this and divide out the mass from every term, and it goes away. And now we're left with an even simpler formula. GH initial is equal to 1/2 V final squared plus GH final. And now we have to figure out what we're trying to solve for, and we are trying to find her speed at the final point. So we're looking for V final. So now we can solve for V final. So we'll subtract GHF from both sides. And we have GHI minus GHF is equal to 1/2 VF squared. We can multiply both sides by 2. That will cancel that 2 out. And then we have 2, I'm running out of space here. GHI minus GHF is equal to VF squared. And then we can square root both sides. So I'm actually going to take this back up to the top here. Let's put it right there. All right, so this leaves us with V final is equal to the square root of 2 G times H initial minus G times H final. And we can plug our numbers in here. So 2 multiplied by 9.81 multiplied by the height initial was 65 minus 9.81 multiplied by 45. And I didn't bring my calculator, but it looks like we have, let's see if I can do this. I got my phone calculator. I just snuck off into a different room so that it was quiet. 9 multiplied by 60. I'll have to do it in stages. I apologize. You can skip to the end if you want to. $637.65 subtract 441.45 is 196. So in everything in brackets here is 196, and I'll multiply that by 2. And that gets me the square root of 392.4. And then I can square root that to become 19.8 meters per second. So that is her speed on the other hill there. Hopefully that made sense. So it is a lot about, all your conservation of energy problems are going to start here. You can build it out and hopefully eliminate some of these. There's 4 terms, right? EK initial, EP initial, EK final, EP final. Hopefully some of those you can eliminate. Especially in this case, if we looked at the snowboarder dropping all the way down to height 0, then that EP final is 0. So there's a lot of different ways you can go about it. Cool, we'll do lots of problems in class. That's the only one I'm going to do on the video. Thanks for watching. Don't forget to like and subscribe.